Hello, everybody. Welcome to the section on operating with time series models. In this video, we'll take a look at stationarity in time series. Now, in the previous section, we had altered the data through differencing, which meant that we took first difference, second difference, or difference from the mean. And we also looked at the data in terms of percentage change and log transformation. And the reason why we were doing this was to make the data stationary. We were taking a look at the mean and the standard deviations. So you notice that the mean got closer to the zero or standard deviation got smaller. So let's head over to the Jupyter Notebook. Now, to start off, I want to say that in certain situations, you may need to make stationary your data. But there are certainly no hard and fast rules, and you can achieve stationarity when you remove trend and seasonality, such that you have constant mean and variance. And in particular data domains and situations, and in your own industry or field, your time series data may need to be made stationary before applying any statistical analysis. But be aware that even weekly stationary data can also be acceptable. So, of course, you can always work with the original data and then compare those results against the data that has been made stationary. So let's check for stationarity of our transformed data sets. We're going to do our imports, pandas, matplotlib. And a formal way to test for stationarity is called the augmented Dickey-Fuller test. And the way this test works is that there's a null hypothesis which claims that the time series is non-stationary due to trend. And then when you reject the null hypothesis, you're then able to claim that the time series must be stationary. So I'll show you how this works. Our first example is the vacation data set. And recall that we took the first difference. We simply subtracted away the values next to each other, and that first data point was removed. We dropped the NA. Now, to apply the augmented Dickey-Fuller test, we want to use AD-Fuller, and that's why up above we had imported from stats models AD-Fuller. So be sure to do that. Now we're going to use the data frame vacation, and then the column name is first difference. When we print out the test statistic, it sits at index position 0. And then for the p-value, that will be at index position 1. And then the critical values are found at index position 4. So we have the critical values for the test statistic at the 1%, 5%, and 10% levels. So what you have here is the test statistic right here, which is negative 3.64. And if you take the absolute value of that number, absolute value, exceeds the absolute value of this number right here, that negative 2.878. You also can see that the p-value is very small. It's 0.005, which is less than the threshold at 5%. So what you can say is that the p-value is statistically significant. We can reject the null hypothesis that our time series is non-stationary. Therefore, we can claim the series must be stationary. The next example is the furniture data, and recall that we took the percentage change. And this is the data that was in millions of dollars. So what you can say, so let's read that in. And so now we're going to take the AD-Fuller test on the furniture data frame, and then the data itself is the percentage change. We're going to get the test statistic, the p-value, and the critical values. Again, if you took the absolute value of the test statistic, it exceeds this number, 2.87. We also notice that the p-value is 0.0165. That is way below the threshold of 0.05, which is 5%. So we can reject the null hypothesis of non-stationarity, and we can claim that the data must be stationary. The next example is the Bank of America adjusted close stock price data. And recall that we did the percentage change, which refers to the return. Now we're going to run the augmented Dickey-Fuller test, obtain the test statistic, the p-value, and the critical values. And so here again, this time the p-value, it's e to the negative 16, way below 5% threshold, so we can for sure reject the null hypothesis of non-stationarity. So we say that this time series is stationary. We're going to read in the JP Morgan adjusted close stock price data. We took the percentage change, which means it's the return. And then we're going to run the Adey-Fuller test. We're going to print the test statistic, the p-value, and the critical values. And again, the p-value, the second number here, e to the negative 28, which is way below that. You're going to have a lot of zeros after that decimal point, 0.000, way under 5%. So again, statistical significance, we can reject the null hypothesis. The time series data must be stationary. Now for example 5, average temperature of St. Louis. And remember, this data was difference from the mean, and that was referred to as anomaly. So we'll read this data in. This is a type of differencing from the mean. And we run the Adey-Fuller test. We obtain the test statistic, the p-values, and the critical values. And again, the p-value, e to the negative 0.5. You're going to have some zeros after that decimal point, and that's way below 5%. We can reject the null hypothesis. The series is stationary. So in summary, all 5 series have stationarity from either first differencing, taking the percentage change, calculating the return, or taking the difference from the mean, the anomaly. And so the augmented Dickey-Fuller test verifies this for us in a very formal statistical manner. So that's all I have for this video.